We begin this section by looking informally at the property that a curve and its tangent line exhibit similar behavior near the point of tangency. We then make observations more precise and turn to the problem of finding extreme values of a function f. For example, in this figure, the line L, this line here, is tangent to the graph of the function f at point P. Note that L has a positive slope. It rises vertically as it moves from left to right. The graph must exhibit the same rising property near x equals a, or this point here. In terms of the function f, we see that as x increases through this point, the value of f of x also increases. Since the slope of the tangent line at P is the derivative, we conclude that if the derivative is positive, f is increasing at a. Inversely, at this point Q, we see that the slope is decreasing, meaning that the function is also decreasing. And then here, at point R, we see that it remains the same. It means it is constant. The slope is 0. It is not changing. Now a definition. Let function f be defined on an interval L, and let x1, x2 denote numbers in that interval. F is increasing if f of x1 is less than f of x2 wherever x1 is less than x2. As we saw, if the slope is rising as x is rising, then it is increasing. F is decreasing if f of x1 is greater than f of x2, where x1 is less than x of 2, meaning that if the slope is downward, as the values increase, the slope decreases, f of x decreases. And then f of constant when f of x1 equals f of x2. For example, here we have an increasing function, a decreasing function, and a constant function. This increasing function, we can see that x1 and x2 increase positively, moving from left to right. F of x1 would be here, and f of x2 would be up here. They also increase, so this function is positive and increasing. This decreasing function shows that x gets bigger, but f of x gets smaller, therefore it's decreasing, and at this point they are the same. It is constant. We are also concerned with maximum and minimum values of a function, or the values f of a number x or c, which are the highest and lowest. F of c is the maximum value of a function f if f of x is less than or equal to f of c for every x, meaning all values of the function are less than the value c. Conversely, f of c is the minimum if f of x is greater than or equal to f of c for every x. We can see this illustrated in the next slide. This function, f of c, has all values of x, f of x less than it, therefore it has to be a maximum. Similarly with this, f of c, f of x is always going to be greater, therefore it's the minimum. The extreme value of theorem states that if f is continuous on the closed interval from a to b, then f takes on a minimum and maximum at least once in that interval. For example, there are local and global maximums and minimums. The term local is used because we localize our attention to a sufficiently small open interval containing c such that f takes on the largest or smallest value at c. For example, this would be a local minimum because in this interval from here to here, it is the smallest value, but we can see from here in all these values that it is not the smallest value overall. Therefore, it is called a local extrema. We also have global extrema, which in the sense of the entire function is the lowest or highest point. For example, here is the global maximum as well as a local maximum, and here is a local and global minimum. This is a local max and min as it is constant and doesn't change. Therefore, in this interval from here on, it is both the highest and lowest value. Numbers at which the derivative is either 0 or does not exist play a crucial role in the search for extrema of a function. We give these numbers and associated points on the graph of the function special names. We call them critical points. A number c in the domain of f is a critical number on f in f prime of c equals 0 or does not exist. Our guidelines for graphing and finding extrema of a continuous function is first to locate all the critical numbers, or the numbers where the derivative is 0 or fail to exist. We then calculate the value f of c for each critical number, calculate the endpoint values, which can be critical numbers, keep in mind, and then find that the maximums and minimums are the largest and smallest values out of these calculated numbers, including criticals and endpoints.